So in this video, we're going to talk about how to find or state the domain of rational functions. As you recall from the definition, it's right there in the definition. A rational function is a fraction. The fraction where we divide by 0 is an undefined number. So the domain is going to be all reals so any number will do, but then we're going to also exclude several values. The values that we're going to exclude, these A, B, and C's in here, are going to be the values that make the denominator 0, thus making the function undefined, or that value, that number, undefined. Let's look at an example. I'll use the one that we have here in the book. Okay, so we want to state the domain. So what we want to find out is we want to say that the denominator cannot be equal to 0. So I want to solve that polynomial equal to 0. So we think back on how we solve polynomials equal to 0. The first thing I can try is to factor. And I'm going to write equal 0, even though we know it cannot equal 0. I just, when I'm solving equations, I like it to be equal to. So I'm going to look at what numbers multiply to -6 and add to -1. And that's going to be +2 and -3. So I chose to factor for this method of solving this quadratic. Then I can set each factor equal to 0, because if two things times each other, two factors equal 0, they become independent of each other. If one factor equals 0, the whole thing equals 0. It doesn't matter what the other factor is. So my two solutions come from each factor. So I solve. And remember that these are the x values that make my denominator 0. If I plugged them in, if I did f of 3, in the numerator I would get 3 plus 1, and the denominator I would get 3 squared minus 3 minus 6. 4 over 9 minus 3 is 6. 6 minus 6 is 0. That number is undefined. If I did f of -2, I would get -2 plus 1 over -2 squared minus -2 minus 6. So I would be getting -1 over 4 plus 2 is 6, minus 6 is indeed 0. So both of those make those numbers undefined. Therefore, the domain is going to be all x such that x is an element of the reals, and x could not be either one of these values.
I heard it went great.
Okay, so that is our domain. If you're asked to write it in interval notation, you could say the domain is from -infinity to -2, union -2 to 3, union 3 to infinity. I think the book will ask for interval notation. I don't really care which notation you use. You need to watch. There could be, there are rational functions that have domain of all reals. That means the polynomial in the denominator, so this is example 2, it doesn't quite matter what I have in the numerator, right? The polynomial in the denominator will never equal 0. So when I say that cannot equal 0, well, that will never happen, because if you think about it, whatever I square comes out to be positive, and when I add 8, I could never get 0. But if you, and by the way, we're talking about reals. Obviously, there's complex numbers that can make that 0. But if I try to factor, right? I can't come up with a number here to factor because it's not a difference of two squares. If I did the quadratic formula, my discriminant is negative, whoops, yeah, I'll do that. Negative b is 0 in this case, squared, right, no, sorry, it's just b squared. I'm sorry, b squared minus 4, a is 1, c is 8. So I would get negative 32. That would mean that that proves to me for sure that my zeros here are complex, because that would be the part under the square root. So therefore, there's no real number that I can plug in here that would make the denominator 0. So we could say that the domain for this rational function is all x such that x is an element of the reals.